All right, kia ora koutou, ko Douglas Walker, toko ingoa. It's my pleasure tonight to introduce Andrew Sargent. Some of you will know Andrew from his YouTube videos or as a classroom teacher. Andrew now teaches at Takura, and he's agreed to make 3 one-hour webinars in preparation for the Level 2 physics exams. So we're kicking off with mechanics, and just before we start, I'll ask if you could please keep the chat for any questions related to physics. And as you pop those in, I'll keep an eye on them, and then I'll either interrupt Andrew as he's going, if they're particularly time sensitive, or I'll collate them and I'll ask them at the end. All right, without further ado then, Andrew, thank you very much, and I'll hand over to you.
Kia ora koutou. I probably don't need to do an introduction because Doug has already done that. I'll just quickly share my screen. Which screen do I want to share? Screen, which is screen 1. Try that. And I'll chuck that up on the there, and I'll just minimize that and get that out of the way. Hey, we can see it. Sweet. Right, and I'll present quickly. Cool. So in the chat, I have chucked the link to this. I can see that a lot of you guys already found this. So I'll just go through this as just like a brief sort of schematic of mechanics. So I'll just put out first great resources. So I've got my channel, which is my YouTube channel. It has all my videos for the last 5 years. Mr. Wilbley, he's got an awesome channel, arguably better than mine. He probably spends more time making my videos. So I'll put the physics folder, which has a lot of PowerPoints. There's a simulation site, which has really good simulations run by GeoGebra. Circuit simulator, not helpful for now, but I'll just use the same PowerPoint for the next tutorial on Friday, and then there's physics realm as well. So mechanics is split up to essentially 3 topics. You've got motion, momentum, energy, and force. And then what I did is I spent some time and I split up the last 5 years. So the last 5 years exams, so 2015 to 2020, is it 5, 6? Anyway, so each subtopic, so I don't know, free fall under gravity, a question that relates to that is the 2017 question 2B for momentum and energy. Let's just pick a random one. I couldn't find any that directly related to work in the last 5 years, although some of the power and conservation of energy questions do kind of bleed into work. It's a little bit, yeah, they're not like hard and fast clarifications. There's a lot of impulse and force questions, and then the projectile and motion questions pretty much are all just one question. So 2015 question 1, the whole question was projectile motion. 2016 question 2, the whole question was projectile motion, and so on and so forth. So without further ado, I think that's really about it. So this is just like, so if there's like a topic or something that you don't quite understand, so for example, balance talks, someone asked in the chat, mentioned talks and how they work. These are all the questions that relate to that question. So yeah, so it pretty much turns up every year, and some years slightly more difficult than others, but there we go. And you'll notice unbalanced force and acceleration, I sort of couldn't really find a question that exactly matched that, but there are a lot of questions that probably could have gone into that, such as like the force components that would have related to it. Anyway, so what I'm going to do is I'll just make it down. Oh, this is the folder that you can see it now. I'll open up. I was going to work through the 2014 exam. I'll just see if I can find it. 2014. I hope that's the one. Here we go, and I'll open up my calendar. And right, so when I go through this exam, I'll like let you know like which topic it pertains to. I've got my calculator up so you can see like how I set up my equations and so on and so forth. So for the most part, the last 3 years or last 4 years, mechanics has just been a 3-question exam with A, B, C, D. One of them is an excellence question, one of them is a merit question, or two of them are usually merit questions, and one of them is achieved. Typically, the first question is always achieved, but that's not a hard and fast rule. But anyway, so we'll start off. So Rachel drops a ball from a balcony. It takes 1.2 seconds to reach the ground. Calculate the impulse on the ball during the time it takes to fall. So impulse is also known as change momentum. So we write the impulse. So there's an impulse formula on your formula sheet. That's one thing I forgot to open up. I'll see if I can find it. I forgot to open up the formula sheet. Give me a second, because I'll try and go back and forth. Just bear with me. There we go. Right, so we have the impulse. I'll just double check. Can we see my mouse? No, we can't see my mouse. I'll quickly comment on that instead. Now let's move this down. So we'll zoom this in a little bit. Mechanics. Right, here we go, and I'll grab my pen. This here is the impulse formula. But you can also just use a general momentum formula, and we'll get onto that soon. So we got impulse is the change in momentum, which is equal to the force multiplied by the time. And you could also write it as just the regular momentum formula, and you can just say change in mass, because you could change the mass if you wanted to. Normally don't, but you could, and then change in velocity. So in this case, we could look at it and we say, well, we know the mass is constant, so we'll get rid of that change in mass. The velocity does change, but we'd have to use a kinematic equation to figure out that change in velocity. It's probably easier to use the force multiplied by the time. So the force is just the gravitational force, because gravity is acting on it. And just up here, the force equals mass times gravity, or it equals ma. I just quickly skip that step, but the acceleration is gravity, and you can sort of swap them out. Right, so the force is the mass times gravity, which is going to be 0.6 multiplied by 9.8. I get the 9.8 because in your formula sheet you have the acceleration due to gravity is it's not actually on the formula sheet. It's probably at the top of here, probably. It's normally on the formula sheet. It's normally somewhere. It's given to you. I know that. So multiplied by the time, which is 1.2 seconds. And that is equal to, so we'll do that on my calculator, 0.6. With a graphics calculator, you can skip the 0 times 9.8 multiplied by 1.2, and that equals 7. So when you get your answer, write the full answer first. So 7.056, and the units for momentum, so with the units for change in momentum are hidden in the formula. So you've got mass, or change in mass times velocity. So you could have kg meters per second, or you could have Newton seconds, because we have a force multiplied by a time. So you can choose either or. I'll use Newton seconds. I use kg meters per second because I was halfway through writing that, meters per second. And now your final answer, we write down the bottom. So we say, we try and do it meter this time. Change momentum is equal to, and now we round to, we've got 2 SF here, we've got 3 SF here. So we round to the lowest amount of significant figures, which is just 2. So it's going to be 7.1 kg meters per second. Right, there we go. Next question. Is the momentum of the ball conserved as it falls? So before we even start that, we say, well, what is momentum? So we write the formula. Momentum equals mass times velocity. And we ask ourselves, has the mass changed? No, it hasn't. Has the velocity changed? Well, it kind of did. It started off at 0 because it was like Rachel was holding the ball. Then she dropped it. So because the velocity has increased, so a lot of students often do this error to say that some value has increased. Don't do that. Avoid doing that. You've got to write the actual words. So I'm not going to write it out just because I'm going to save time and try and get through as many questions. You can just listen to it. So you would say, because the velocity has increased when it was dropped, momentum is not conserved. Momentum is only conserved under the presence of no external forces. in this case, the force of gravity acting on the ball is an external force, which has accelerated up the ball, full stop. Right. There we go. So next question. I'm just looking at the questions on the stream. Hope everyone can hear me. Right. So next question. Rachel throws the ball. So it has a vertical component of 9 meters per second and a horizontal component of 12 meters per second. So this is pretty much a projectile motion question. I can see off the bat. I mean, if you've got split velocities, it's going to be a projectile motion question or something similar to it. So state the vertical component and vertical component of velocity and the horizontal component of velocity when the ball reaches its highest point. You may ignore. So this, when it says you may ignore air resistance, it is you will ignore air resistance. So the vertical component at the top, it's going to slow down, then stop. So the vertical component at the top is just going to be 0 meters per second. And the explanation. So I'm not going to write it out. I'll just talk it through. So the explanation is, as the ball moves under its own inertia upwards, it's constantly decelerating at 9.8 meters per second until the ball stops. And then it accelerates in the other direction or downwards at 9.8 meters per second until it hits the ground or until something hits it. The horizontal component, I didn't actually check what the horizontal component is. Okay, it's 12 meters per second. So the horizontal component is 12 meters per second. So we'll just check the question again. So when you're doing these questions, it pays us to check the actual question. Just make sure that you're asking what it's you're answering what it's asking. So state the vertical component of velocity. Yep, I've done that. And then the horizontal component of velocity when the ball reaches the highest point. Yep, I've done that there. So the reason why the horizontal component is still 12 meters per second is because we are ignoring air resistance. That means there are no horizontal forces acting on the ball, so the horizontal velocity won't change. Because remember, force equals mass times acceleration. So if you have 0 forces, you'll have 0 accelerations. You'll have nothing to slow the ball down. Right, that hopefully answers that question. I'll just go up to the chat and make sure I've seen everything. Cool, no. Right, next question. So that previous question was sort of a projectile motion question, but not really. So it comes under the branch of it. Right, when the ball is compressed, it acts like a spring with a spring constant of 1200 newtons per meter. When Rachel throws the ball against the wall, it compresses to 9 millimeters. So you can either divide this number by 1,000 to get 0.009, or something to that regard, or you can just say that, or you can write it as 9.0 times 10 to the negative 3 meters. That's called the engineering prefix. You can just Google it, and it gives you the whole millimeters, macrometers, micrometers, nanometers. I can't remember the rest of them go. It's a 2014 exam for those that are asking. Right, calculate elastic potential energy stored in the ball when it is momentarily stationary against the wall. Calculate the maximum possible speed at which the ball rebounds. State any assumptions you will make. So I'll quickly fire up the formula sheet because we probably need it. I'll just show you where it is. So we have these are the energy formulas. So we have spring potential, which is the first formula. We have the kinetic energy, half mv squared, which is the second formula in the middle. And then we have the gravitational potential energy on the right. So yeah, so they're the only three. And you also have work equals force times multiplied by the distance. And you've got power as well. But we're just looking at potential energies or energies at the moment, not conversions of energies. So what we could do is calculate this. Well, EP is equal to half, and it was kx squared. Kx squared. We have the spring constant, that's k. We have the compression, that's x. And that is pretty much all we need. So 0.5 multiplied by, just double check everything, x like a spring, 1200 meters. We need the mass. No, we'll need that later, so it's going to be 1200 multiplied by, I'll just shorthand it, 9 times 10 to the negative 3, and that is going to be, I'll put the equal sign down here. Just a small side note, seeing as you guys have been doing this exam, to try not to write in this column here. It's a bit annoying for markers when, I suppose, it's not really for you guys, but it's for the markers. It makes it nice for them. When they're containing these papers, it just makes it easier if you try and write everything in the lines. So we'll clear that on my calculator. So 0.5 times 1200 multiplied by 9. And this EXP button, if you've got a graphics calculator, the EXP button is a shortened version of going times 10 to the power of. And then we're going to go to negative 3, and then we can go squared. So if instead, I should probably actually cover this, if students do this, times 10 to the power of negative 3, and then you go squared on top of it, you'll get not a syntax error, but it'll do the order of operations just from left to right, and you'll get the wrong answer. So if you do it this way, you make sure you have to put brackets between the number. There we go, and we get 0.0.0486, and it's joules. That should be a J. It's a bit funny. And then over here we write EP is equal to, we'll round how many? 2 SF. 2 SF. So we need to round to 2 significant figures. So we're going to go to 0.049. 0.049. And that is joules. And now maximum rebound speed. So now we're going to have the potential energy is going to be equal to the kinetic energy. And our assumptions made, there's no energy lost. So we're going to have a completely elastic collision, and there's no energy lost at all. And all the potential energy is going to be converted to kinetic energy. All the spring potential energy is going to be converted to kinetic energy. I hope I said that right. Right. So the formula for kinetic energy is just half mv squared. We're going to try and find the maximum rebound speed. So we're just going to move the half to the other side. So we're going to have 2 times EP. We would have been left with mass times velocity squared. Mass is multiplied by velocity. So to undo multiplication, we need to use divide. So divide the left-hand side by the mass. And this would be equal to velocity squared, but we want to undo the squared so we can get the velocity. So we'll square root both sides and we get left with the velocity. I'll quickly check the chat. No, we're good. Right, so we chucked in. So this is when it pays to chuck the numbers. When you're doing this actual exam, put the actual numbers in. It's quite messy because I'm just using a stylus, but if you're using pen and paper, it's a lot cleaner. 2 times, all right, 0. Actually, use the unrounded value in your actual equation. So 0.486, it's a bit messy, but it's right, divided by the mass, which is 0.6. And then if I do this on my calculator, how am I going to do this? I'll quickly clear this. And I want to go to multiply shift answer, because it's the previous answer I had, so it's saved at 0.0486. Most calculators can do this. What we'll do, we'll go equals divided by 0.6 equals shift square root, shift answer, equals 0.402 meters per second. And then we can just chuck down here the velocity. So this is our unrounded value. And then down the bottom, our velocity is equal to, round this up to 2 SF, so 0.42 meters per second. Right, and I'll quickly just check the stream whilst I'm at it. There are no questions. No, we're good. Right. so that is that question there. It is a conservation of energy question. So in that PowerPoint, if you look up conservation of energy questions, you'll find questions similar to this. So if this is something, if going from, or yeah, if this is something that you're struggling with, you can just find similar questions that have the videos to go with it. And yeah, just the assumptions made, total elastic collision, and that all energy was conserved. Cool. Next question. Jamie is doing a workout. He's using a barbell with weights on it. Total mass of the bar, total mass of the bar with the weights on it is 120 kilograms. Calculate the work done on the bar if Jamie lifts it 0.55 meters vertically at a constant speed. Right, so in your formula sheet, okay, there are two ways to do. Oh, did I write something wrong? Oh yeah, there should be an M, meters per second. It's like an M here, meters per second. Yeah, it's hard to write with the mouse. Right, back to what I'm doing. So come to your formula sheet. Let's find those energy formulas. So we could think about it. It's gained gravitational potential energy, because I assume he lifted it off the ground. He lifts it off the ground. So it's gained gravitational potential energy. And we could calculate the work that way and just say the gain in potential, the gain in gravitational potential energy is lost by Jamie, or we can just use a work formula, which is force times distance. So we'll do both, I suppose. So work is equal to force multiplied by the distance. The force is the force of gravity. So if we'll just sketch up a little barbell. We're going to have the force of gravity acting downwards. That's Fg, and then we've got Jamie's lift force acting upwards. We'll call that F lift. I don't know. So you're overcoming the gravitational force. You're providing that lift force. So we could do it that way, which would just be equal to mass times. So force equals mass times acceleration. The acceleration is due to gravity, which is just going to be g, multiplied by the distance, and that is equal to 120. I scribbled on that, but it doesn't really matter. Multiplied by 9.8, multiplied by 0.55. This formula here is pretty much identical to the EP formula. EP equals mgh. You can see that in this case, it's just D instead of H. So the formula is basically the same thing. Oh, it should be changed now. It's delta H. There should be a delta in there. Is it 9 or 90 in times 10 to the 3? Oh, it should be 9.0, but I just left out the 0.0 because it wasn't needed. Before Sleepy goes to ask that question in the chat. It's 9.0 times 10 to negative 3. Right, so back to here, and I'll do this on my calculator. Clear 120 multiplied by 9.8 multiplied by 0.55 equals 680. Was it 646.8 joules? And then we're going to write down the work down the bottom. So our final answer, 2SF. So this is where NCEA can be a bit funny. This ordinarily should be rounded up to 650 joules. That's a funny way to write 50. But it should be rounded up to 650 joules. However, oftentimes the mark is, this is why it always pays to give the unrounded answer first, then the rounded answer as your final product, if that makes any sense. So yeah, there's never been a question for quite a few years about getting SF correct, but it pays to just try and. Will you lose marks for decimal rounding errors? No, you won't. In fact, you don't even lose marks for not having the units. A bit annoying, but in the time that I marked for NCEA, we're never penalised for not even having the units. So, yeah, what you will lose marks for is if you round too early in a question. So this is probably something to touch upon. This previous question here, if you had rounded your energy, so if you'd used a rounded version of the energy of 0.49 in the second equation, you would have got a different velocity. Or it would have been slightly off. Maybe it was 0.39. That would have caused you, this is definitely an E question. that would have caused you likely to go from E to an M. So don't round until you get to the very end. Only give rounded final answers, and still give the unrounded version just above it, just to show that you can demonstrate understanding, and then you give your final answers. Yeah, it's a bit of a sticky topic. There's no real, I haven't had any real clarification on that. Maybe Doug could probably comment on it, but anyway. Right, next question. Jamie puts a barbell on 2 supports and changes the weight on the bar with no weights on one end, the 30 and a 30 kg weight on the other end. The support force provided by the right hand support 0. So there is no force acting here. Draw labeled arrows in the diagram showing the forces on the bar. Use the concept of torque to calculate the weight of the bar. Assume it is a uniform bar. Cool. So it's a uniform bar, which means the center of the mass, or the center of mass of the bar is going to be acting in the center because it's uniformly spread. So I'll just find the center somewhere here, and we're going to have that. Okay, when you do these vectors, because I'm trying to do it, can I use an actual? Oh no, I can't use a rule. I've got a touch screen. I can't use it because it might mess up the touch screen. Use a ruler for this. So you must use a ruler, and you label things. So this is the force of gravity acting downwards, and we're going to have the force of gravity acting on the weight. That should be a straight line. You should be using a ruler, but I'm just doing it on my touch screen, so I can't make it straight. Can I do line? No, it'd take too much time. So we have our forces acting downwards. There is no force whatsoever acting on the right-hand side, but there's a support force on the left-hand side. So this is holding up the bar. And we can just chuck that in. And there we go. And it is in equilibrium. Yeah, it must be. Yeah, so it hasn't really said it, but it's not moving. So, or it's moving at a constant velocity. So, like a little tip, you'll never really get marked. Oh, you might get marked on it. The sum of the downwards arrows equals the upwards arrows. So this arrow here should probably be slightly larger, or maybe these other 2 arrows should be slightly smaller. Because it's a vector diagram, you should be able to sum the arrows. The arrow up plus the 2 arrows downwards should equal 0 because it's in equilibrium. Right, and now
you're talking about force there, Andrew. There would still be a force at what you've identified as the pivot, though, wouldn't there? It's the torque that you ignored there.
Right, in the center here.
No, if we're using the right hand, which pawn are we using as a pivot?
We're going to use the left hand side as a pivot.
Yeah. Okay. So just on the point of forces, there you mentioned some of the upwards forces equal some of the downward. Yeah. Sorry, I shouldn't have interrupted there.
Yeah, that's fine. No, it's a good thing to clarify. So it can get a little bit confusing. I'm bleeding torques into forces, but I mean I don't know whether they'd mark you for it. So I'm never really seen you get marked down for not having the correct size of the vectors for as long as they're kind of within the ballpark. And if I ask you to do a vector sum diagram, then yes, they have to be the correct sizes. But they'll have a question below that'll ask you to sum up the vectors. How do you know which point is a pivot point? Then you got to sort of visualize it. So you'd say, if one end was lighter or if one end was heavier, what does it pivot? In fact, no, you could actually choose. You could choose whatever point you want, and then the forces are calculated from around that point. Probably not the easy. This question isn't the best to decide which pivot point to use. I wonder if I could probably. I'll use this left-hand side as a pivot point, and then I'll see if I can use the right-hand.
Well,
I can do both.
It's in the question, isn't it? And this is where when I interrupted earlier, it's because the right-hand support is 0. There's no upwards force there, so the only point you can use as a pivot, I think, would be the one that you've marked with the upwards forces.
Check the weight of the bar. Yeah, because we don't know the size of the support force on the left-hand side. So we wouldn't know.
On the right is 0.
Yeah. Well, we could work backwards once we find it and find the support force, but then it'd be a bit superfluous. So we'll just, you could, if you tried to use the support, if you tried to use this as a pivot point, you wouldn't know what this vector here is. So you wouldn't be able to solve an equilibrium question for it. That's how you know, like, which, yeah, that's how you know you can't figure it out. And you don't know the mass of the bar either. So we're trying to find that out. Right, quickly. This is going to be our pivot point right here. I'll probably just circle that one more time. This FG will make the bar spin clockwise. So we're going to call this TC for clockwise. And then from symmetry, this weight will spin it anti-clockwise, AC. So then normally the first thing you always do is, because it's a torque question, the anti-clockwise torques should be equal to the clockwise torques in equilibrium. And then torque is just force times distance, or it is mass times gravity times distance. So we're going to have the mass, I'll write it out, mass times gravity times the distance of the weight is going to be equal to, there's only one other thing, which is a mass of the bar times gravity times the distance to the bar. I probably should have had chuck a wee subscript W there and W there. Yeah, so that's why I've used that as a pivot. Right, so now we'll just I'll just put a break here. The mass of the weight is 30 kilograms times 9.8 multiplied by, how far away is it? 15 centimeters, so 0.15. Always got to do things in meters, is equal to, this is 45 centimeters from the pivot point. So it's going to be equal to, and we don't know the mass of it, so we just leave the mass as question mark, multiplied by 9.8, and then we're going to multiply. I'm going into the column, but it's only because I'm using a stylus. So when you do this, try not to go into the column. Multiplied by, and it is 0.45. 0.45. Right, so you can see I can divide both sides by 9.8. It cancels that out. I'm going to write it down here. I'm going to have 30 multiplied by 0.115, and then I'll divide both sides by 0.45. That should be a 0.45, and that will be equal to my mass. And then I'll quickly calculate that out. So clear, 30 times 0.15 divided by 0, well, just 0.45, because my calculator can do that. And we get 10 kgs equals 10 kgs. And then calculate the bar, assume it's a uniform bar. So we're going to have, we've done the label. Okay, so when you do this, you wouldn't have drawn all over this like I have. So for this question here, this first part, there's a diagram at the very bottom. If you draw it all over like I have, you need to go to the very bottom and redraw your vectors with a ruler, and use concept of torque. So we've done that as well. So the weight of the bar, so we'll just call it the M of the bar, is equal to 10 kilograms. And then we ask ourselves, is that reasonable? Yeah, that's pretty reasonable. Right. So if that came out like 100, I mean, when was the last time you ever saw like, well, that wouldn't make any sense. Bars at gyms wouldn't weigh 100 kilograms. It just wouldn't make sense. We've got a forces thing. So we got, after doing some weights, Jamie goes across the punch bag, which is a large bag hanging from a chain. The mass of the bag is 35 kilograms. Pulls it horizontally. Yada yada yada. Draw the three forces acting on the ring at the top of the bag. So we'll do that first, and then we'll come back to that question. So, okay, I'll draw that on the actual, like the actual picture. So we're going to have the mass of the bag. This is where, I'm going to actually try to use a ruler on the screen. See how it goes, shall we? Oh, that's kind of hard to do it. Acting downwards. And I'll do the labels at last, and this is going to be acting sideways. Okay, stuff that. Ruler's just slipping all over the screen. And we're going to have the force of tension acting upwards. Now, these don't have to be to scale, simply because this is just like a guide, because when you do your vector diagram, then you'll do it all to scale. So this is just going to be FG. We'll quickly see if they gave us labels for things. Okay, I'll just call this C for chain, and F for rope. And then you'll need to do a key. So we'll do a key over here. FC is tension force of chain. And then that should be a C. And then FR should be, why is that? There's meant to be an R. Should be tension force. So I've chucked some tension force of the rope. So when you do these vector diagrams, a lot of times kids don't do keys, which it's not super necessary, but it's quite helpful. And FG, you can obviously write down the force of gravity acting on the bag. So we'll go back up to the question. It's not moving. It says it's probably in equilibrium. Yeah, so it's an equilibrium. So these vectors will sum to 0. So we can have we'll just try and split this into 2. The vector acting downwards plus the vector acting exactly horizontal plus the vector acting up to the right equals 0. In other words, if we go downwards and then can I delete this? Yes, I can. I'll quickly rub that out. I'll quickly rub that out because I realize I'm going to the left next. There we go. Quickly swap back to my pen. Doesn't matter. Oh, does it rub out with my actual rubber? Oh, it truly does. That's magic. Right. So we need to go, we'll do it over here. Down the gravitational force. And we are going up the tension force in the chain. And we are going, this needs to go right up to the top because my horizontal force is exactly, so the force of the rope is exactly horizontal, and that needs to go, I don't think it's out of order.
The tension force might be in there.
Yeah. I've done this out of order. This is what happens when I'm not paying attention. Can I rub this out? Right. Talking as I go. There we go. So I've done this one first, then I should have done this one. I was just talking and getting confused. And then I need to do this one here, which is just back up to the top. There we go. This is FG. This is the force of the chain. And then this here, angle here, is going to be 30 degrees because they've given it to us. It's just over here. And then I can bet you they're going to ask what's the force of, during vector addition diagram of the 3 forces, determine the size of the tension force on the chain. So the tension force, which is F force of the chain, is the hypotenuse. The gravitational force is the adjacent. So if we have the adjacent and the hypotenuse, we're going to use cos from SOHCAHTOA. So first we write cos theta is equal to the adjacent divided by the hypotenuse. And then we say that's equal to the adjacent is FG, G divided by FC, force acting on the chain. This is probably where I shouldn't have used C because that's typically used for centrifugal force, but I've got my key up the top left. So if an examiner was looking at this, they'd be like, he's written the key, that's fine. And now we need to rearrange for the force on the chain. So we'll move FC up. So we'll multiply both sides by the force of the chain and then divide both sides by cos theta. So we're going to have I'll just write this here, force of the chain is equal to the gravitational force divided by cos theta, and that is equal to mass times gravity divided by cos 30, and then that is equal to, what's a mass? What is a mass? 35 kilograms. So 35 multiplied by 9.8 divided by cos 30 degrees. And then we'll do that on my calculator. 35 multiplied by 9.8 equals divided by, okay, I couldn't quickly check, shift setup. Okay, I need to go down and change my calculator to degrees. So we go exit cos 30, 396. I hope that's right. I hope my calculator changed on the fly. 396.0, that should be 0.06 and newtons, because that's the units of force. That should be an N. We'll just double check what the question was asking. Determine the size of the tension force on the chain. 396, that seems legit. You've got a 35 kilogram chain, so it should be roughly in the ballpark of 350 newtons acting straight downwards, and because the chain's on a bit of an angle, you'd expect it to be slightly larger, and because it's hypotenuse, you'd expect it to be slightly larger than 350, or it'd be slightly less, it'd be like 340 something. So this seems reasonable. So down the bottom, we can just put F, force of the chain is equal to, we'll round this up to 2SF probably. Yeah, everything's done in 2SF, so we'll go 3, that'll be 400. Round it to 400. It doesn't really matter as long as you've got both sets of answers there. So normally they just mark the most correct answer. So that should be 400 newtons. Right. Next question. Jamie punches a bag. Hopefully I've got everything right. How to know where the angle goes for the vector diagram? You can sort of prove it to yourself. So you can actually draw that's a really good question. If you go to the actual picture, you can draw the force of gravity acting downwards like so, and then we can draw the rope force mapped onto it, and then you can see that the 30 degrees is at the top. That's how you know. So you can actually sketch them straight onto the actual picture they do. Probably make your diagram a bit better and obviously neater because you're using a pen and won't be drawing on a computer screen like I am. Right, quickly check any more questions. No, there we go. Oh, yeah. So when you do vectors, it's nose to tail. Jamie punches the bag horizontally. He puts on a glove with a thick padding and punches the bag with the same velocity. Discuss the difference between the punches in terms of the stopping time of his fist, the force on the bag, state any assumptions you make. So he punches it horizontally, then he puts on a glove with thick padding and punches the bag again with the same velocity. So this is an impulse question. And the way you can sort of tell is impulse is to do with time and force. So if there's any question that has sort of like time, and the impulse questions are never, or sometimes they can be slightly vague. So if you've got force and time, you know that you're dealing with impulse is equal to force multiplied by time. So that comes into that PowerPoint that I had where I had all the impulse questions. You can just go and click on them. I haven't put links yet. You can just search them on YouTube. It's not hard to find. Eventually, probably by Friday, I'll have links that you'll be able to easily find. So I'm not going to write it out. I'll just talk about it. In both instances, the impulse is going to be the same. So he's coming in with the same velocity. So his impulse to stop, because he's going to be stopping his fist, is going to be the same. So that's your first sentence. You'd say in both circumstances, the change in momentum is the same. In the situation where Jamie has thicker padding, the thicker padding will increase the time of collision, thus will decrease the force acting on his fist. Force on the bag. Decrease because the force on his fist is the same as the force on the bag. It's Newton's third law. So decrease the force on the bag, full stop. In the instance of him punching without gloves, the time of collision will be shorter, thus increasing the force acting on his wrist or acting on the bag, I should say. Full stop, and that's pretty much it. So that's impulse. I mean, there's lots and lots of questions. The best impulse question that I've written up is the 2019 scholarship exam, question 5D. It's a level 2 concept, but it was in the scholarship exam. If you look that up, it has the full possible answer, but you can also look on the PowerPoint. It's got lots of examples of impulse, and it's pretty much the same question every time, just different context. Right, 3. Shamila and her car have combined mass of 100 kilograms. She's driving at a constant velocity. Calculate the size of the vertical force the road produces on the car. So she has the car and her have a weight force. Change of P is the same for both because that's a good question. Punches a bag again with the same velocity. So, but sometimes that's a good question. Sometimes they don't actually tell you. So you have to, not infer it. You have to state it. So you'd say, I am assuming both situations the impulse is the same. So a lot of the times that's actually a really good question. A lot of this is like the thing that kids miss is they don't say, I am assuming in both situations that the change in velocity is the same because it's the same situation. So you have to state that. It's like one sentence. You can just like throw it out there, and that covers your base. Right, calculate the force she produces on the car on the road. That's just you're going to have the gravitational force acting downwards. That's Fg, and then the support force is going to act upwards, and those two vectors will be equal. And that's going to be Fs. So those two vectors are going to be equal, which means the vertical force produces, vertical force the road produces on the car is Fs, but that's just equal to Fg. So we can write, this is a bit tedious, but we can write Fs is equal to Fg, which is equal to mass times gravity, which is equal to 1100 multiplied by 9.8. I could do that. 1100 times 9.8 equals a large number, equals 780. 780, and that is newtons because it's a force. And then down here we'll have F R for rho, or F S I suppose, equals 10. We're going to round this up to 2SF, so it's going to be 1100. 11,100 newtons. Right, if you're European, you use a full stop, but we're not, so we use a comma. Well, something that's German, use full stop. Anyway, that's regardless. Shamila says that even though the car is moving at its equilibrium, explain what the state would mean. So I'll just explain it. So equilibrium means the sum of all the forces add to zero, which means the net. So if the sum of all the forces add to zero, the net force is equal to zero, and that means the net acceleration is zero. So it's not accelerating, and it means it's just moving at a constant speed. And that pretty much explains that. Would the thick padding increase the mass? It totally would. I just saw that in the chat. However, we're just kind of ignoring it. You could even say, I'm ignoring the increase in mass from the thick padding. It is a good question, though. Right. Short time later, Shamila car accelerates from 2 meters per second to a speed of 22 meters per second. She covers a distance of that, 72 meters. Calculate the size of the average net force on the car while it accelerates. So to find that, we're going to find the acceleration first, and then we'll just multiply the mass, and that'll give you your force. So this is a kinematic question. I think this comes under accelerating in a straight line. I think it's like the first slide in that PowerPoint that I gave you. Right, so this is where you write out like what things are. So from a speed, this is the initial velocity. I normally just draw on the actual numbers, but you can just write VI equals 2. Maybe I'll do that. VI equals 2, so that's the initial velocity to a speed of 22 meters per second. So that's the final velocity, or velocity final. It's equal to 22. I'll leave the units out. Covering a distance of 72. And we want to find the acceleration so we can find the force. Because force and acceleration are essentially proportional. You've got the whole F equals ma, which you're probably getting sick of by now. So to find out the acceleration equals question mark, normally I tell my students to write the variables that you have, go to your formula sheet, and find the one that has all the variables. So we say, well, this one has time, we don't have time, we don't have time, we don't have time. This is the only one that has the variables that we need. So we go back in, we write that out. Vf squared is equal to Vi squared plus 2AD. And then we rearrange for the acceleration. So we're going to subtract VI from both sides, and then we'll divide both sides by 2D. So we're going to have VF squared minus VI squared divided by 2D is equal to A, and that is going to be equal to, I'll put the numbers in actually, 22 squared minus 2 squared divided by 2 times 72. 2 times 72, and that is equal to, we can do that calculator. So we have 22, 22 squared minus 2, minus 2 squared equals divided by bracket 2 times 72 bracket. I'm putting all these brackets here and I'm doing equals to try and avoid syntax error. I mean, you can sometimes rely on your calculator, but it's just good to be extra cautious. This is an exam, so it pays to be extra cautious. So we got 3.33, put a dot here, meters per second 2 squared. So it's meters per second or meters per second squared. And then we need to find the force. So down here, force is equal to mass times acceleration. The mass of the car is, I'm sure it's 1100 kilograms. Yes, 1100. So 1100 times 3.33. And here we'll just go times 1100. Oh, no, delete. 1100. Bingo. Equals 3666.66 newtons. And then down here we have F is equal to, round this to 2SF, because everything else is done to 2SF, or the lowest amount. That's 2, that's 2, that's 3. So we round to SF. So we're going to have 3,700 newtons. Right, I can see that time's getting on, so I think we have one more question to do. I'll just scroll down. Right, so this is just a weighted question, so I can blast through this quickly. She drives a car around a corner. Drives a car at a constant speed around the corner, then drives over some ice. So let's highlight some things. Constant speed. She drives over some ice. So this is no friction. No friction. I should say it's friction, but I'm trying to go as fast as I can. You can assume there's no friction between the ice and the tires. Cool. Describe the net force, if any, before and after she reaches the ice. Explain how the net force affects the motion of the car before and after she reaches the ice. So this is where you can split the answer into the first half, which is when she is on the road, and then the second half, which is when she's on the ice. So the net force when she's on the road is, because she's changing direction. So because she's changing direction and she's moving at a constant speed, she's accelerating. So acceleration is just a change in velocity. Velocity is a vector, has size and direction. In this case, the direction is changing. It's changing to the to a right, I suppose. So here is it's turning to the right. I'm just like projecting myself into the car. So this is the force, and just because force is equal to mass times acceleration, it's going to be accelerating to the right as well, which is changing its direction. So you just say, right, before she reaches the ice, she has a net force which acts towards, I suppose you can call this a circle, which acts towards the center of the circle. That net force is provided by the tires. It is a center pointing force, bracket centripetal force. One thing that really annoys me, or that I suppose a lot of times students say the centripetal force changes the car's direction. It doesn't. Centripetal force is just a brand of force, just a name for a type of force. It's the friction of the car's tires that change the car's direction, which, because it's pointing towards the center of the circle, because it would make the car go in a circle, it comes under the branch of centripetal forces or circular pointing forces. Centripetal just stands, it's Latin for center pointing. And explain how the net force affects the motion of the car beforehand. So you say, sort of explain that it'll accelerate the car to the right, or it'll change the car's direction. When she hits the ice, there is no net force because there's no friction. So the car will continue on in a straight line, tangent to the circle. So it'll just continue on straight. Right. next question. Hopefully I'll blast that. There's lots of questions like this that I've put on the actual on that PowerPoint that you can find. I think there's one more question.
I wouldn't stress over time too much, Andrew, as long as you don't have any pressing commitments. This will be recorded, so anybody who needs to go can go.
Yeah. I'll finish this whole exam because it pretty much covers everything. The last thing for me to do is momentum anyway. So calculate. Well, I sort of did a little momentum before, but that was mostly impulse. Calculate the total momentum of the car, which has got a velocity of 18 meters per second. So your formula for momentum is just mass times velocity, which is going to be 1100 multiplied by 18. And then it's going to be equal to clear 1100 multiplied by 18. And that is equal to 1980. And the units are mass times velocity. So it's going to be kg. The units for mass kg and the units for velocity are meters per second. So they're the full units. And then we write down here P is going to be equal to, or momentum is equal to 20,000, because we're going to round up to SF, which would mean we need to round up to 20,000. So 20,000 kilograms per meters. Kilogram meters, that should just be kilograms. Get rid of that. Can I rub that out? Kilogram. Oh, that's messy. Kilograms meters per second. That is super messy, but that should read kg meters per second. Little unrelated, could you tell us what papers you'd be covering for electricity waves so we can answer the papers before coming to the webinars? I'll probably do the 2014, and if I have time, 2013. It's just because I've done 2020 back all the way down to 2015. So it doesn't make sense to redo papers I've already done. This is 2014. Calculate the size and direction of the car as it slows down from 18 meters per second to a velocity of 11 meters per second. So this is where, there's a bit of a misconception that I'll throw up in here. So we're going to have change in momentum is equal to, there is no change in mass, so we'll just leave it as regular mass, multiplied by a change in velocity, which is equal to mass times, and then change of velocity, remember from, I think maybe year 11, so it's the final minus the initial, VI, which is going to be equal to, mass is equal to, whoops, I should put the numbers here. Rub that out. It's getting late. That's why I'm making mistakes. What is the mass? 1800. Okay, I'm going to rub that up because I'm going to have to draw that whole thing. So we're going to have 1100. 1100 multiplied by, what's the final velocity? Is 11. Final velocity is 11. Totally is. 11 and minus 18. There we go. And that is going to be equal to, and I'll quickly do that with my calculator, 1100 multiplied by 11 minus 18 bracket equals negative 7,700 kg meters per second. And so this is when it says size and direction of the momentum change. I mean, the direction's kind of given by the negative number, but this is where you can use it in words as well. So you can say size is equal to, we don't need to round that at all, 7,700 kg meters per second, and then direction, I suppose it's backwards because we don't actually know if it's going to the right or the left. Does it say? Slows. Maybe I don't know, backwards. Backwards. Woods. I say backwards, but I'm going to try. Maybe I should have said opposite direction to the car was traveling. That's a bit of a wordy sentence. But you get the drift. It's the opposite direction to which the car was traveling. But it's given away in the negative sign. Shamila puts her foot on the brake, the car slows down. Explain the principle of energy conservation in this situation, and identify the transfer of energy caused by braking. So she had kinetic energy. So she had EK, and she's losing it to, I suppose, the brake pads are probably slowing her down, and the friction of the tyres as well. I don't actually like this question because if you like, I'll break it down. I'll tell you the answer, but then I'll tell you the full answer. So, principle of conservation: you're going to convert kinetic energy to the sound energy and heat energy of the brake pads. The brake pads will heat up, and the tires will probably heat up as well because you're transferring energy to the road. But that's the answer. In reality, however, you're going to be you're so small. You're going to be adding. You'll be losing your kinetic energy to the rotational kinetic energy of the Earth. However, the Earth is so small, so big compared to you. You're not really going to change its velocity at all. So you will actually lose some energy to the, I would imagine, to the Earth. I always find it hard to believe that it's all turning into heat and friction. You'll add a little bit to the Earth, but I mean, it's not going to notice. It's kind of like if you jump up in the air. I mean, you push down the Earth, but it doesn't move because it's so big. So in terms of the structure of this question, kids could probably go overboard and maybe overthink it, but it's just you're losing energy to the heat of the brake pads heating up. And the friction on the tyres and stuff like that, and they'll heat up as well. Right, calculate the average rate at which the brakes transfer energy as the car slows down from a velocity of 18 meters per second to velocity of 11 meters per second in a time of 6 seconds. So this is power. Calculate the power. Opposite the velocity, Ben Rocket. Yes, way better than what I said. Yeah, that's a far better, more succinct way to do it. So the way to solve this question is there's two ways to sort of do it. You can find the acceleration, and then from there find the force, and then just go. Okay, I'll do it first. So you'd find the initial kinetic energy, find the final kinetic energy. Minus the difference, and then power is equal to work over time, and that would give you your average rate of energy transfer. We'll do that. We'll find the difference in the kinetic energy first. So we're going to have EK final minus EK initial is equal to the change in energy. And what should we do? We'll go half M, and it's going to be the same mass. It totally is going to be the same mass. Yep. M V final squared minus half V M. Oops. V initial squared, and then we can pull out the common factors. We can pull out half M, and then we're going to have V final squared minus V initial squared. You don't have to do that step, but it's just nice and easy. And that is going to be equal to half. What's the mass? It's like 1100. Pretty sure it's 1100. It hasn't changed. Half 1100. So multiplied by 11. Oh, that should be 1100. And then we're going to have final, which is 11 squared. That should be 11. Oops. Minus 18 squared. 18 squared, and that is going to be equal to, so I'll do the squared first, so I'll go 11 squared minus 18 squared, and that equals minus 203, and then we're going to multiply that by 1100, and then we're going to multiply that by a half. It's a little bit backwards, but it's just an easy way to do it. So we have, well, this is just an energy, so we can get rid of the negative sign because there's no such thing as negative energy, but it tells you that energy was lost. So that it tells you that there was kinetic energy lost, but we'll just scrap that negative sign. So we're going to have, what number is that? It's 111,000. So 111, 650 joules. And then because in a time of 6 seconds, we're going to find the rate, which is the energy per second. So we're going to get the rate is just per second. So it's just going to be the change in energy divided by the time, which is essentially power. If you go to your formula sheet, you've got power down here, which is work over time, and work is just change in energy, because to do work, you're changing energy. You're going from one form to another. So we're going to have that number. I'm not actually going to do it because I've got it saved on my calculator, divided by time. So we're just going to go that number divided by 6, and that equals 18,608. 608.3, and this is going to be joules per second, because I went energy divided by time, so my units are energy divided by time. Energy is joules, time is seconds, and then we need to finally quickly round the very end. We're going to have, and this is power, so we're going to have P is equal to, we'll round this up to 2SF, because we're 2SF. So it's going to be 19,000 watts. So watts are the units for power, named after James Watt. Right, that is really about it. So if there's any burning questions in the chat, Doug, that you had, let me know. Otherwise,
I think you've answered them really well all the way through.
Cool.
There were some questions at the beginning about torque in terms of, I think somebody was talking about a bridge problem, and there was one with the diving board, but I think they should be able to apply the principles that you've outlined for the barbell one to solve those. And I think you've probably got I know there's a diving board question in one of the exams that you've probably
got. So the bridge question is the 2020 exam. It's last year's exam. There is another bridge question somewhere, and the diving board question is, when was that? That was 2017. I've got it in the PowerPoint, so if I can probably, where is the PowerPoint? Here. These questions here are all the talk questions. Hopefully by Friday, I'll have hyperlinks to all these, but until then, you'll just have to use YouTube and search it. It's not super hard.
You can probably link those to the No Brain Too Small if you did want to put the links in.
Yeah, I'm just going to link them to the videos which go over it, and then inside the descriptions have the actual. Yeah, I was going to link them to the videos. They have the walkthrough. I'll use Mr. Woodley's ones for the 2020 and 2019. I'll just use my ones for the rest. But they have all, and then inside the videos have the papers. Have the papers plus the answers.
Yep.
So yeah.
Awesome. Well, thank you very much, Andrew, for a very well prepared set of resources and wonderful working through the exam, especially from somebody who's had a bit of experience as a marker and can add that extra value there. So for everybody who's watching, you've got heaps of resources on Andrew's YouTube channel, which was linked in the webinar document, and we'll hopefully catch up with you for the waves and electricity papers, which I think are both on Friday night. And the links are in the webinar. So thank you again, Andrew. Really appreciate all your time and expertise in this, and I hope it benefits the students. Hope you get a chance to go and put your feet up now and catch you on Friday.
I'll just close off. There was one person asked a question